So in the last lesson, we looked at a couple of problems and there was a function and we wanted to know how the function behaved at some point x is equal to a. Okay. To know this, we chose values of x and we got closer and closer to x is equal to a. We looked at values of x that were on both the sides, like left side and right side of x is equal to a. We saw the function values were approaching as x gets closer and closer, like this. The function value is approaching. And guess that this function value is the value we are looking for. Okay, suppose this is L. So this process is known as taking the limit. Or taking the limit. We will make a notation for this. We need a function fx and also a value of x that we are moving it towards. So limit of fx is L as x approaches a and we write that limit x tends to a fx is equal to L. Provided we make fx as close L, we want for all x sufficiently close to a from both sides without letting actually x is equal to a. So limit of fx is L as x approaches a, and we will write it like this: limit x tends to a, fx is equal to L, provided fx is as close to L so fx is as close to L as we want for all x values which are sufficiently close to a. Without letting actually x is equal to a. Okay. So as per the definition above, we chose how near we want fx to be from L. And suppose we want to make our fx within 0.0001 from L. So fx minus L is less than 0.0001 where fx is larger here. So this distance, the distance between them is not greater than 0.0001 and fx is larger than L. And then L minus fx is 0.0001. In that case, fx is smaller than L, like this distance. So this distance maximum it can be 0.0001. Fx is smaller than L. Okay. If we get x sufficiently near to A to make one of the above inequality true. So x should be sufficiently closer to A to make any of the above inequality true. So so we can say that there is a value x here, okay, capital X, so that for all x's that are closer to A than x, there are values of fx which are within the range of 0.001 of L. So in order for limits to exist, we get fx as close to L as we desire, like 0.001 in this case, for some x which will be needed to stay in that closer and closer within the range. We can say that as x gets nearer and nearer to x is equal to A, from left hand side and right hand side, then fx must be getting closer and closer to L. Like this. We have to look to both sides of A, left hand side and right hand side, but not at A. The limit is only concerned about what is going around A. So as fx tends to L, x tends to A. X is not A, but maybe slightly less than A or slightly greater than A. So as x tends to L, as x tends to A, x is not A, but maybe slightly less than A or maybe slightly greater than A. So if if it is shown like this, then A is approached from left side of A. Like this is a graph, this is A. So A minus means this side. And x tends to A plus. So that means that when A is approached from, so this is a graph. Okay. So we can say that A is approached from this side. This arrow is like this. So limiting value of the function. Limiting value of function. So we can consider a function like fx is equal to x square plus 3. And we want to find the limit at x is equal to 3. So value of the function at 3 would be 9 plus 3, so 12. If x it tends to 3 minus, means we are approaching 3 from the left side, then we write limit x tends to 3 minus x square plus 3. This is called limit value of function fx when x tends to 3 minus. So we can replace x by 3 minus h, okay, where h is a positive and very small value close to 0. So when h tends to 0, x tends to 3 minus. We are subtracting a very small positive value from 3. Okay. So it is, suppose this was 3. So we are from this side. So this is, we are subtracting a very small positive value from 3. So the limit would be so h tends to 0 because suppose this is h distance here. Our x is h distance. So x tends to 3 minus means x is moving towards 3. So the distance between them is h, which is going towards 0. Okay. Because x is equal to 3 minus h. So as x is moving towards 3, h is moving towards 0. So this would be 3 minus h square plus 3. Which will give limit h tends to 0, 9 minus 6h plus h square plus 3. So this would give limit h tends to 0, 12 plus h minus 6. So when h tends to 0, okay, it doesn't become 0, but when it tends to 0, then h minus 6 tends to 0 minus. Okay. So if we put here 0, we can say that a very small amount will be deducted from there and limit. So this will be like very less amount here of h minus 6. So it will be approximately we can say 12. Okay. However, it is not exactly 12, but it is slightly less than 12. Suppose we put h as a very small value, like h is equal to 0.00001. So h into h minus 6 would be 0.0059999. Okay. So now limiting value of fx when x tends to 3 minus. Okay, limiting value of fx when x tends to 3 minus is slightly less than 12. Since 3 is approached from left hand side, this limiting value of the function is called left hand limit at x is equal to. So this is left hand limit at x is equal to 2. So now we want to find limiting value of fx when x tends to 3 plus or right hand limit. So limit x tends to 3 plus x square plus 3 and limit h tends to 0. So this is limit h tends to 0, 12 plus h plus 6. So this will give us 0.00006 and so this will give us around. So left hand limit and right hand limit are not exactly 12, but these values are approximately equal to 12. That means the behavior of fx is same when x is approached from both sides of 3. That is to approach 12. So we can say that limit x tends to 3 fx exists because from left hand side and right hand side both it approaches 12. So suppose this is 3, so this would be 3 plus h, and this is 3 minus h, and this is 12, and this is 12 plus k, and this is a very small value k, 12 minus k. So we observe that 3 minus h, so minus h, x minus 3, or if we put in the absolute value form, we can say absolute value 3 minus x minus 3 is less than h. So if when we have this, then we get 12 minus k So this would give us minus k fx minus 12 is less than k, or 0 fx minus 12 is less than k, where k is a very small positive value. So the more and more we make the interval less, or compress the level 3 minus h to 3 plus h, if we make this more and more less, the interval between 12 minus k and 12 plus k is squeezed, and we get limiting value of fx closer to 12 when x tends to, so x tends to 3. So fx gets closer to 12 when x tends to 3. So the last example what we saw is the above example was defined and it was continuous everywhere. Now we can take another example like this, and find the limit of x tends to 2 for the function x square plus 4x minus 12 and x square minus 2x. So to find the left hand limit, we put like x is equal to 2 minus h. Okay, the function we are finding from 2, so this x is somewhere h less than 2. Okay? So we'll put h tends to 0, and this will put as x 4 2 minus h minus 12, and this is 2 minus h square minus 2 minus h. Okay, so this gives us limit h tends to 0, and this is 4 minus 4h plus h square, 8 minus 4h minus 12 and 4 minus 4h plus h square minus 4 plus 2h. So when we simplify, we'll get limit h tends to 0, h square minus 8h and this will be h square minus 2h, which will give us limit h tends to 0, which gives 8 by 2, which is 4. So here we can say that h tends to 0, h is not exactly 0. Okay. Similarly, we can get right hand limit. Okay, limit x tends to 2 plus, and same way x square plus 4x minus 12 and x square minus 2x. So this will give, since this is the graph, this is 2, so x is greater than 2, and suppose this is h distance. So we'll put x is equal to 2 plus h. So limit and h tends to 0 because x tends to 2 plus, it is going towards this. So this will be 2 plus h square, 4 plus h minus 12 plus h square minus. So this is 4 plus 4h plus h square and 8 plus 4h minus 12. 4 plus 4h minus 4 minus. So this will give limit h tends to 0 and this will give 8h plus h square over 2h plus h square. Okay. So here we can see that left hand side and the right hand side limit both are equal to 4. So behavior of the function from both sides of x is equal is same, though the function is not defined at x is equal to 2. So the limiting value of function fx here is when x tends to 2 is equal to 4. Okay. Okay. Though fx is the function value of f, though f of 2 is not defined. Or it doesn't exist. So we can take one more example, like if we can consider function fx over this, and we want to find the limit around x is equal to 0. So basically we are finding the behavior of fx in the neighborhood of x is equal to 0. So left hand limit is limit x tends to 0 x. So finding behavior of the function in the left side. So here it would be, so x is equal to 0 minus h. And so the function is at 0. So this is from left side. So just h is a very, very small distance, but we are approaching from left side. So this would be limit h tends to 0 factorial of, sorry, absolute value h 0 minus h this will be 0 minus h over 0 minus h. So limit h tends to 0 is equal to factorial h, which gives limit h tends to 0. This will give us h is a very small positive value. So this is equal to h because h is a small positive value. So this becomes, and this becomes h over minus h, and this is equal to -1. Now for right hand limit, here we are approaching 0 from the positive side. So limit x tends to 0 minus 0 plus, right? So this would be absolute value of x or x. This is h tends to 0. Here it is 0 plus h. This is a small distance h. This is x over 0 plus h. So this gives limit h tends to 0, h over h. This gives 1. So we can see that left hand limit is not equal to right hand limit. So we conclude that the limit of function fx at x is equal to a exists if the limit of a function fx at x is equal to a exists if x tends to a minus fx is equal to limit x tends to a plus fx, or we can say limit h tends to 0 f a minus h is equal to limit h tends to 0 f a plus h, and the limits exist. So this left hand limit needs to be equal to right hand limit, though the function may not be defined as x is equal to a. Okay. Thanks, and we'll continue in the next lesson. Thanks for joining.